Thank you. Good morning, everybody. So I will introduce you today a few works that have been done in our group to try to characterize humans in general. And so I will start with the description of a work on re-identification of a human that has been conducted by Vladimir Sommers, Alexandra Lai from EPFL, and myself. And then I will go on with 3D pose estimation, but I will come to this a bit later. So first, re-identification. So the problem consists in trying to answer this simple question. Given two images of a person, we have to decide whether this corresponds to the same person or not, the same individual or not. And this problem is useful to solve different kind of application, to address different kind of applications like retrieval in a large data set of humans, for example, in a video surveillance network. There you provide a query, you can, from the query, retrieve all the images that correspond to the same individual in the database. Another application of re-identification is tracking. When you want to track a human along the time, across the time, space and time, if you are able to recognize, to detect individuals along in each frame, basically the tracking problem becomes an association problem, and this can be solved using re-identification. So how is it generally formulated? This is illustrated in this slide. So you see that the formulation consists in trying to represent each image of each individual based on an embedding vector in some feature space that has been learned and designed in such a way that the re-ID problem becomes trivial. And so what you try to do in this space is that the feature vector that correspond to an image are the same, are close to each other using a Euclidean distance simply, if they correspond to the same human, and they are far away from each other if they correspond to different humans. So if you are able to build such embedding space, it becomes quite easy to solve the re-identification, of course. So in our team, what we have tried to address is focused on two main issues that appears when you try to use re-identification tools. The first one is related to occlusions. So when you encounter occlusions, you have difficulties to characterize the human if you use a global descriptor. This is illustrated here on the left side of the figure, where you see that you have a query that contains a human, but also this human is partly occluded by a car, and you see that the retrieval is misled by this car, because you retrieved image in your database that include the car but do not include the same human than expected. Occlusions also occur in tracking context when you have multiple people occluding each other. So of course. So this is an important issue when you want to use re-ID in practical applications. And then another problem that we have addressed is the specificities that have to be solved by re-ID when dealing with tracking, for example, typically. And this is illustrated in this image by the fact that when you are dealing with tracking, in general, you are facing a group of people, and you have a prior information about the human that are part of the scene you are analyzing. And this prior can be used to decide which features are especially discriminant to differentiate individuals in the scene at hand. So this is generally overlooked by re-ID problem, which try to discriminate a given human from a large and huge data set. Here in tracking, because you are in front of a small group, you can really focus and decide to adapt the descriptor to the fact that in your scene, you might have a similar appearance, but some aspect of the appearance might differ from one individual to another. And so this is the problem we have tried to address to make ReID more effective when included in a tracking pipeline. Okay, so the first issue is related to the occlusion problem, and so the main problem comes from that if you go in the literature, you will notice that most of previous methods use global descriptors, so they try to associate a feature vector or embedding vector to each individual, and this descriptor is global. So this leads to this kind of problem that I mentioned earlier. And so our solution to address this problem was to try to design a system in which we do not generate a global descriptor, but we try to generate part-based descriptors. We were not the first to try to address the problem in that way. This is a natural way of doing. So previous work have tried to do it, but I will try to tell you what are the specificities of our particular solution. So working based on parts has an advantage. It's the fact that you can only rely on the visible parts when you try to infer, to decide whether two images correspond to the same individuals or not. Of course, you can ignore invisible parts, so it means that you should predict not only a descriptor per part of your body, but also a visibility index that tells you whether some specific part, here for example the legs, is visible or not. And this will help you to use properly this part-based descriptor. Okay. So, so what were the challenges, the main challenges to deal with when designing a part-based descriptor? They are illustrated here. And you see that one of the challenges was that in the ReID data sets, you have a large set of images in which you have a label indicating for each image to which individual you are referring, but you do not have human parts labels. So you do not have a segmentation of the body parts in your data set. So this is one issue. And another issue is that the label that you have for an image tells you which individual is present in your image, but does not tell you whether the given parts of the body is discriminant or not. So it's illustrated here. For an example, you see that you have two different individuals on the right side, and anyhow, they have the same appearance, body appearance. So if you just transfer the global ID label to the part label, you will, during training, try to differentiate those two body appearance. And this is not relevant, of course, because the body appearance, in terms of just the body part, the appearance is exactly the same. Okay? And so this is one big issue when you train a part-based model. It's the fact that the labels that are available from your training set cannot be directly provided to decide how to train the part descriptor. Okay? And so what we have designed is an architecture that is a bit depicted here in a simple way. So you see that in the first part of the architecture, you just have an encoder, a pre-trained network. Here it's a ResNet 50 that will be used to encode the input image. And then you have a specific head that has been designed to predict for each region in the image whether it corresponds to a specific part of the body. And you have also a prediction of the visibility or invisibility of your body part. The main contribution of this work consists in the design of the losses. So you see that you have two losses. One is related to the ReID problem. So it will try to ensure that descriptors that correspond to different identities will have different representation in the embedding space, and that descriptors that correspond to the same identity will correspond to the same vector or similar vector in the identity space. But as I told you previously, one issue here is that you cannot, the part-based descriptor cannot inherit directly the label from the identity of the human. And so you have to design this loss very specifically to make it robust to this problem where you have two different persons that have body parts that are visually similar. So you should not, in that case, force the network to separate the descriptor associated to those body parts. I do not go in the details of this loss design due to lack of time, but you can go to the paper and you will see how it has been implemented in practice. So another contribution was related to the body part definition, and this is the PP loss. So this is the partition loss. And this loss basically use a human parsing label that comes from an external model that provide raw partition of a human in parts. And this raw part, despite the partition is relatively coarse and not very accurate, we use it to bias the construction of descriptors to fulfill, to respect this coarse human parsing label. In final, we end up in a system that becomes able to use attention on specific parts to characterize the human. And here, if I take the same query as considered previously, you see that indeed the network will focus on the body parts that are relevant and will use only those body parts to implement the retrieval process in the database, leading to a correct rank 1 selection. Okay, so this is about the occlusion of a human by an object, but then there was still an issue remaining when considering practical ReID problems, and this issue was particularly problematic in case of tracking and association in a tracking context, and this is related to occlusion by a human. Because in that case, the problem becomes more tricky in the sense that you see that the attention of the network will be spread between the two humans that are present in your image. And so the descriptor that you will extract from this image will be a kind of mix of the appearance of the two individuals that are present in the scene. This is, of course, problematic, especially if you are in a tracking context. What you would like is to detect the two humans, but in general, the detectors detect a bounding box. The bounding box will probably, in that case, include the two humans, and so you will have a wrong descriptor. So there, to solve this issue, we have considered a way, so this is illustrated here, but I will not go much more in details. So we have considered the use of prompts to feed the network and indicate to the network which humans interest us in the image. So this is illustrated in this image. You see that the prompt in red corresponds to the human we are not interested in, while the prompt in color illustrates the key points of the human we are interested in. Those key points in practice are generated by a 2D pose estimation model. So this can be provided from an external model. This also can be provided manually, and in the paper we illustrate a different validation procedure depending on the scenario that provide the prompts. But you see that by using those prompts, we can really indicate and lead the network to use the correct attention and to focus its attention on the correct human and lead to a correct retrieval process. Okay. So how is it implemented in practice? So we start from the initial architecture and we add a few components. So those components consist in a part that will basically extract the key points from the input image, and it will decide which set of key points correspond to the human we are interested in and which set of key points does not correspond to the person we are interested in. Those key points and the image go through a tokenizer, and they are encoded and processed by a pre-trained swing transformer. So here the swing transformer is named MS swing simply because it considers a multi-stage fusion to keep the resolution, high resolution in the token process. Because the swing transformer in general, if you take an off-the-shelf swing transformer, it reduces the resolution of the token maps along the process. And here we wanted to preserve a high resolution of tokens, so there is a small modification of the architecture there, but this is not the most important. The most importance lies in the fact that to achieve good performance using this architecture, we had to introduce two contributions. One was a specific data augmentation, because if you consider conventional ReID dataset to train your model, there are few cases that indeed include occlusions. Among the large set of images available, only a small fraction consider occlusions. So we have created occlusion artificially simply by superposing two images of humans. And this helps us to provide more difficult samples during the training of the network. And then another contribution was this tokenization process that fusion the information from the image and from the prompt to lead the classification and the part-based and the attention mechanism that extract the relevant part of your image. Okay, and so if we look to the performance we can achieve, and here, of course, I show an increase of performance on a data set that has been a bit specifically designed to include this kind of problem. This is why you have a large gain, but more important than the absolute gain, which of course depend on the kind of data you have to manipulate. If I give you a data set where you have no occlusions, the gain will be zero. But what is interesting is to analyze how this gain is spread across the different components of the network. And this is illustrated here. So you see that the fusion and the token helps a lot. And also the data augmentation process contributes significantly to the increment in performance you can achieve by this architecture. Okay, so now I have rapidly gone through this problem of occlusion. I will try to give you a flavor of what needs to be done to make ReID appropriate to tracking problems. And therefore, what you need to understand is that when you deal with tracking and you involve ReID into tracking, it's important to take the context into account. And by context, I mean the scene, the characteristics of the scene you are dealing with in terms of motion, but also in terms of objects that are present in the scenes and in terms of their specific appearance. Okay, and so the tracking problem is based here. We have formulated the tracking problem as an association problem. So we assume that we detect the object along the time, and then we try to associate the objects that are detected in a new frame, in the current frame, with the trajectories that have been built in the previous frame. Okay, and in general, what people are doing to solve this association problem is that they extract some cues from the trajectory, cues from the current frame, then they define a kind of metric that mix the motion cues, the appearance cues, and they get a matrix that a distance matrix that will measure the distance between detections and trajectories, and you can use an Hungarian algorithm to decide which detection should be associated to which trajectory. This is the conventional way of doing. But what we would like to do is design a system in which the weight you give to the motion and appearance change depending on the scene at hand. And we would like also to make the representation of the object specific to the group that you are dealing with. So here you have an example that is illustrated. You are considering tracking in a sport event. Of course, the dressing of all the shirts and the shorts of all players is the same, so it's not discriminant at all. But what you see is that the shoes of the player here is discriminant, simply because you have a group of people in which only one player has the green shoes. So we would like that our method becomes able to figure out that this part of the ReID descriptor is relevant to associate players across the video. Okay, so this has been implemented, and I cannot go into the details, but there is a paper that describes the system. This has been implemented by a transformer that basically takes as input all the features and the representation vectors associated to detection and trajectories, and that will jointly consider all those appearances to build a representation that is more discriminant. And this is illustrated in this example where we visualize the appearance of detection as points and trajectories as lines. And you see that the initial description and representation of motion and appearance cues was not as discriminant as the representation built by our network that exploit the specific scene that is analyzed along the process. So this work has now achieved state-of-the-art performance on a sport data set, especially because it has been designed to be specific to cases where ReID has to be quite smart and accurate to discriminate between body parts and exploit the right body parts to be discriminant. And all those works are summarized. The first two are described in papers already published, and the latest one is still under review, but I provide an archive link and the GitHub related links if you are more interested. Okay, and there is a whole list of publications. So the first three publications correspond to what I have surveyed now, and the rest are related publications more specific to sport analysis, since this project was partly funded by a sport company. Okay, so I will now switch to the last component of this talk about human characterization, and this is related to 3D human pose estimation. And this has been conducted with a PhD student from our group, Abol Fazal, so Seyed Abol Fazal Kazemzadeh. And the problem is simply consists in trying to figure out what is the 3D pose of a human in a world referential, in an absolute 3D world referential, from several input images. So you have a set of cameras that observed a scene, and you try to extract the pose of the human, so the key points of the human, but in 3D. This is a tool that is relevant for example, neuroscientists that want to analyze the recovery of a patient that had a stroke or some disabilities, and if you want to recover how the patient recover movements, it helps them to have access to this kind of information. And what you would like is be able to place one or two cameras in a hall or in a room, and simply as a push button have a solution that for any position of the camera is able to give you the 3D pose of the human. So this was the objective of the project. If you go to the literature, what you will notice is that most of the works that are addressing this problem consider this setup, in which they consider a data set that has been captured in the lab with a dome of camera, and they start from the image and try to predict directly with an end-to-end approach the 3D pose. The problem is that if you go with this solution, this cannot be deployed in a real environment, because if you go with your camera and go in the room of a neuroscientist, the system will not work, simply because the image you will capture in this room will be different from the training images, and so the model you have trained is too specific to the acquisition setup considered during training to generalize to real life conditions in the wild conditions. So what we have studied is a solution that works in 2 steps. The first step is based on a mature solution that extracts 2D pose from images. So there are many models that are able to do this, and they are quite robust to acquisition conditions. So they can work in the wild. You go with a camera and you, from any image taken in any condition, you can get the 2D pose composed of a set of key points. And what we have tried to do is to learn a model that is able to turn the 2D poses that have been extracted from the image by those models, those off-the-shelf models, into a 3D pose. And so we name this a pose lifter because it manipulates pose at the input and at the output. The advantage is, of course, that it can generalize much better, because if you go in a place, you install your camera, you use the off-the-shelf model to get the 2D pose, and then you are only working on pose, which is exactly what you have considered during the training of your model, so it can generalize better to real world conditions. Okay, but this requires to get access to 2D, 3D pose correspondences, and for this purpose we have built on synthetic data. Synthetic data can be considered here because, again, the generalization issue that you generally encounter is not a problem here, because the mapping from real world to the pose is ensured by an off-the-shelf, robust and solid and quite accurate model. And once you are in the 2D pose referential, you manipulate just points and locations, so synthetically, or whether those points are coming from real image or from synthetic image, it does not make a big difference. Okay, and so what we have done is that we have used a large data set of motion capture meshes, and from those meshes we have generated the training data we need. So we have assumed that we were locating cameras in arbitrary position around the human. From the camera location we can extract using rendering tools a mesh rendered in an image, and we can use the off-the-shelf model to extract the 2D pose from this mesh. Actually, we were positively surprised by the fact that off-the-shelf models work on those kind of meshes, so we did not need to go for more realistic rendering. This rendering was sufficient to get the 2D pose, and what is nice is that this 2D pose estimation is subject to the same kind of noise that will be present at inference time, because we use the same 2D point detector. And on the other side, we can extract the 3D pose simply by regression of the 3D mesh we have chosen, and we have located in the scene ourselves. So we can get the actual 3D pose and get many training samples of this kind. Okay, so this is how we generate the data set. And using this data set, we want to train a pose lifter that will be ideally agnostic of the camera parameters, because what we would like is that our model works whatever the camera location. And so we decide to represent the key points not as an image coordinate, a 2D image coordinate plus the camera intrinsic and extrinsic calibration parameters. We have tried this, but it did not work properly. What we do instead is to describe each key point by a ray of light, the ray that goes through the key points. And this is a line that is independent. Once you get it, it does not depend of the actual location of the camera or parameters of the camera. So we feed the model by parameters that describe the ray of light, which is a universal way to describe the location of the point in the 3D referential. Okay, and so from this, we have designed a transformer-based model. I do not go into the details, but the idea is to first fusion a given key point information associated to a specific key point, for example, the head or the left feet or whatever. And then once we have fusion this information across all the cameras, we fusion the joint information to get the 3D pose. And this helps us to recover missing key points sometimes. So if we have occlusions and some points are missing in some of the two views, for example, the missing points in 3D can be recovered by the fact that we know the location of other key points. Okay, and here you have an illustration of the performance that we obtain on conventional data sets. You see that we improve significantly compared to triangulation, which remained the state of the art for this kind of problem. You see also in green, you have the solution that is camera agnostic, and it performs as well as a model trained specifically for a camera. So this is quite interesting. We do not lose performance by making the model able to handle arbitrary camera location. So it means that the model in green can be used in any kind of scenario, which makes it without needing a retraining. Okay, so there is a list of publications associated to it. I do not go into the detail, but I will conclude on this and leave the floor to my colleague Mathieu Simon.
Thank you, Christophe. Thank you very much for the very nice presentation. And I want just to remember to the attendees that they can really write some possible question on the chat, and I will read to the speakers. But I will leave the floor to the other speaker, and then we will open possible question also among the panelists today. So please, just I give the floor to Mathieu Simon. The title of the presentation is Representation Learning, Disentangling, Identifying the Underlying Factors of Variation.
Thank you. Hello, everyone. So let's just me share my screen. Here you go. Can you see it?
Yes.
Perfect. Okay, so I will present you another work that we do in our lab at UC Louvain, which is a bit different. So I will first start by giving you a bit of context. So imagine I give you a red cube and a yellow pyramid, and I ask you, could I have a yellow cube? And for a human, the answer is obviously yes, because as a human, we have some deep understanding of things as different separate concepts. We have the shape and we have the color. And so we really have some intrinsic concepts here. And we understand the world like that. And the thing is, the success of machine learning generally depends on the data representation. We've seen a lot of progress in machine learning in the recent years. And a lot of that is also driven by the way we represent the data. And so that would be really nice if we could have the same kind of flexibility in the way we represent the data. So we have our red cube, and then we could build a representation model that would separate the different concepts, just as we humans do. So the color and the shape. And that would allow us, for example, we change the color, for example. So some editing applications that could have also implication for compressions, and a lot of different possibilities here. The problem is that if you just try to learn an autoencoder like that and hope it will be disentangled, so disentanglements. It will not be the case. You will obtain a vector, and then the different concepts will be somehow merged into a single vector. And so the task of disentanglement representation learning is it's really asking the question, how can we learn a representation of data such that the different concepts are separated? And for example, here we have facial images, and we would like to separate the hair, the eyes, the skins, and just separate those so we can edit them or just do tasks on only classification on only one part and not the others, things like that. So this is really the goal. And the thing is, asking for disentanglements actually leads to very deep questions, or almost philosophical questions. And the first one is that just the fact that if you ask that you are able to separate the different concepts and you can do it in an unsupervised way, it means that you assume that there is some sort of intrinsic human-free definition of those concepts. So this is already a big assumption. The second problem is that, well, how to be sure the problem is well posed, even if you have different concepts, you need to be sure that they are appropriately defined such that you can recover them uniquely. And the last thing is just that now, even if the two first points are true, you need to be able to build a model such that you can recover those concepts. So really you have three very important questions, and this is related to what we call identifiability. So you want to be able to identify the different concepts. And I could do a whole 2 hours presentation on this. And this is really a pretty complex problem. And so what we did first is to restrict a bit the problem. Instead of saying, okay, we want to disentangle everything, let's try to disentangle 2 parts. And so what we look at is disentanglement representation learning for sequential data. So we assume we have a sequence, so with multiple views of the same thing. And what we will try to do is to separate what is static, so what we call the static factors, which are what is time independent, so what is common between the different views, and the dynamic part, which is what is varying, what is specific to each view. And I will give you an example here. So we have, for example, here 2 different sequences. And what is static is the appearance of the person. And the dynamic part is the motion, the facial expressions, the things that are varying with time. And it just stems from the idea that as soon as we have multiple views of something, we might want to separate what is common, what is shared between the different views, and what is specific to each one. So this is really the idea here. And there are several works that try to tackle this topic, but we had some issues with those. The first one is the lack of a proper non-ambiguous definition of the factors. So as I said earlier, this is some very important, because if you don't know really what you're looking for, often you end up with ambiguous definitions. You don't know what is static, what is truly dynamic. The second is that usually these models, they require a lot of supervisions, and typically like labels, data augmentations, things like that. And we argue that if you have a proper definition of those factors, actually you can recover them in an unsupervised way. And the last thing is that usually they also do a big assumption, that they assume that those 2 parts, they're independent, which usually is not the case. And what that leads to is usually those models, even if kind of simple data sets, such that moving shapes, so you just have shapes that are moving and rotating. And here we try to sample new dynamics, so new motion for those shapes. And you see that it also affects the shape. It's not an ellipse anymore. And so they kind of fail even in simple data set to provide a disentangled representation. And so what we try to do in our paper is to really apply the 3 main points I presented you earlier, which is first, try to formalize the problem really and define the factors. And then from those definitions, we can derive sufficient conditions such that those factors are identifiable. And then lastly, try to build a model such that we can directly fulfill those conditions, and so directly obtain our factors, and that without additional losses or supervisions needed. So unfortunately, I don't have the time to explain everything. I invite you to check out our paper to see this in full detail. I will just try to give you a bit the main core ideas behind the model. So as I said earlier, the idea is to try to separate. So we have the static factors, which is what is common and shared across all time steps, and the dynamic part, which is the motion. And the objective is to learn a latent vector f and latent vectors lambda, which capture respectively the static part and the dynamic part. And the classical approach, what is usually done, is very schematically, like it's far more complex than, but very schematically, it's building an autoencoder model, a variational autoencoder. And at the middle, they obtain a single big vector, and that vector has two parts. They say, okay, the first n dimensions will be the static part, and then the other dimensions will be the dynamic part. And we can already see here why already they really need supervisions. Because if you just do this, well, you could have an infinite amount of different pairs that would lead to the same reconstruction. So of course, it can't really disentangle, it can't really separate things unless you add supervision. And so what we propose is to completely change the approach and build a completely different model that completely rethink the way we tackle this problem. And so the idea, we start by building an autoencoder, but this time with a single fixed static part that will aim to represent those static factors. And so we take our sequence, and then this is the encoder, and then we build a decoder. We explain the decoder later. So what we do is that we take each frame, and for each frame, we will estimate the static part, the static latent code. So we do an estimation from each frame, and then we aggregate those estimations to give us the static code. And so by doing that, it already provides some sort of permutation invariance to our static part of the network. And for now, we assume, let's assume that this perfectly works, right? So this gives us exactly what we're looking for. This is the common information shared across all time steps. And so we assume for now that f is perfectly disentangled. If it's the case, then the dynamic part is kind of the residuals. And intuitively, if we just look at the sequence here, and I give you exactly this, then what is needed to reconstruct each frame is just the difference, is the residual of the image. And this is really the core idea here. And this is why for the decoder, what we'll do is build a conditional normalizing flow. So what is normalizing flow? It's an invertible model. And the normalizing flow will try to model each frame conditioned on the static part. And so what we be left with is the residuals, and so what the dynamic part, if f is correctly disentangled. So the complete model is given here. So this is the all loss. It's just a simple VAE loss. There's no additional supervision needed. And so you have the encoder here, as I've shown you before, and the decoder becomes a normalizing flow conditioned on the static part. And so what we're left with is some sort of residuals. And if f only captures the static part, then this will be the dynamic part. And as I said, there's an important thing is if f is disentangled. So if f perfectly captures the static part. And of course, it's not always the case. So we just need a final ingredient, which is shuffling. So instead of conditioning on the static part, we condition on the shuffled estimations. And this is the only thing we need. And the neat part is actually in our paper, we show that if we do that shuffling operation, we can directly identify the factors. And so we have like proof by experiments, but also directly mathematical proofs that it is identifiable. And intuitively, you can see this here. Just the fact that if you shuffle the static estimation and use them for the reconstructions, you simultaneously force them to be time invariant and informative. So you force them to capture the static part. And for the dynamic part, because this captures the static part, it's just the residuals, so it will be forced to capture the dynamic elements of the sequences. And we have made some experiments, so I can show you just some experiments here. So the idea here is that you can swap the facial expressions here. So you take the images and I swap the facial expressions. You can also take this and we take the appearance of the first column and the motion of the second column, and then we swap them. So we can impose new motions. We can also take sequences and try to sample new appearance for the same motion or new motion for the same appearance. And we can see here that compared to previous models, like for the shapes, for example, now it correctly maintained the shapes. And so the conclusion is that we propose a null formal approach towards this problem, towards sequential disentanglement. And we do that by proposing a new VAE approach that is provably disentangled, and that it goes beyond the VAE framework that is classically done. And we extend it with a normalizing flow, and so that it also, I didn't explain that, but it also generalizes to both dependent and independent factors. And lastly, we show that all of this is achieved through a simple shuffle operation. We don't need any additional loss or complex supervision. It's completely modality free. And so that concludes my presentations. If you're interested, you can check out the paper.
Thank you very much for very nice presentation. I just remember to the speakers, but also really to the attendees, that all the presentation will be available in PDF. And I just asked to the speaker to send us this presentation. Of course, this is also a way just to really give the possibility of all the people just to have the information available for your presentation. I would like just to really open just the discussion with some questions. I don't see any question from the chat. I don't know if some of the panelists want just really to make some question.
I would like to ask something.
Yes, please.
Congratulations to both authors and really great work they presented. And my question is that for this very advanced research, the results are several scientific papers, but my interest is have you implemented some real world problem solving application to that facilitate and use the novel method you provided? Since I believe that there are a lot of applications in both cases, in both approaches, and my interesting is did you start to work on that, and is there any progress?
Yeah, maybe I will reply. Thanks for the questions. Indeed, this is a bit the purpose. So it's ongoing. So we are for the 3D pose estimation. We are now interacting with companies that could be interested, for example, for training. When they train people to handle production process on production lines in the pharmaceutical industry, for example, they want to make sure that the human, the operator, does the good gestures and so on, and all the actions. And so we are interacting with them to develop a solution for this purpose. We are also interacting with neuroscientists, and we have, but in that case, it's more to help them to conduct their own research. So it's not really for commercial exploitation. And about the tracking solution, it's part of yeah, it's considered to be integrated in the products and the tools used by Sport Radar, so which is a company specialized in sport content analysis, and so it will be mainly used for this purpose at this point.
Thank you. Other questions? I want just really to make a question. Okay, I was very, very interested in the presentations, and I would like just to really ask you what you think about possible limitations that you can have in this type of system with the AA Act. Because as you know, the Act just forbids some type of application, in particular some recognition of the person when we use some video camera and so on. And this is the fourth aspect. I would like to really understand from your point of view about A Act and your research work, and of course possible applications. And the other question is always related to the A Act. In the A Act, we talked a lot about transparency of the AI systems. You discussed a little your work in this presentation, and when I see just how you select some types of features in such a way, is a way just to explain the system. But I would like also to have your feedback from this perspective.
Yeah, indeed, this is always an issue when we consider cameras to analyze human behavior. So this directly pops up, and indeed for the 3D pose estimation, for example, we had interest from companies to monitor and to control the quality of production using this kind of tool, for example, but actually it's not really accepted by companies and you know association of workers and so on. They do not want to be supervised all the time. So this is why we are now considering the training, because there is a real interest to improve their training, because it's limited in time and in scope, and this is quite accepted positively. And regarding the tracking and the re-identification, indeed, even if we have used surveillance data to validate and to train our models, the main purpose in our case was the tracking, and the tracking again in controlled scenarios like sport events and so on, for which the actors give their consents. And so this makes it easier from this perspective, but I totally agree that this is a big issue, and this is always a source of discussion when we had several projects in the past involving also scientists from human sciences and in philosophy and so on, and this is difficult to agree on what is acceptable by the society and what is not. There is no definitive answer to it, because everybody has his own opinion, but laws are evolving also, and some have when you have discussion with people regularly, you end up in a situation where people accept in some cases, but not in other cases, and so on. So this is a real important issue to handle and to discuss in the future. Personally, as a developer of solution, what I try to do is to explain the limitation and the capabilities of the systems, but I let those people that have more background and a higher level view on the system to discuss, and I find it's quite interesting for us engineers to get their feedback, because sometimes it's surprising because they rapidly think about alternative usage of the technology, and that might be problematic. So.